In the time it takes to fingers, some release enough energy to power an entire civilization for 4,500 years. So naturally, scientists and engineers have been working to build a miniature star here on Earth to plug in the plug with. And the thing is, we already kind of have. It just doesn't look like a tiny star floating in the lab. The stars are made of almost incomprehensible number of particles which gravity compresses into super dense core. This core is hot and dense enough to force atomic nuclei together, forming larger, heavier nuclei in a process known as fusion. The reverse process, where one atom splits in two, called fission. In both processes, the mass and the end product is slightly less than the mass of the initial atoms. But that lost mass doesn't disappear. It converted to energy according to Einstein's famous equation. And since C squared is such a massive number, both fission and fusion generate a lot of energy. Fusion in sum mostly produces helium nuclei. In most common pathway, two protons fuse to form deuterium nucleus, which then fuses with another proton to form helium-3 nucleus, which then fuses with another helium-3 nucleus to form helium-4 nucleus. But there's a catch. The first step is incredibly rare. Only 1 in 100 septarian collisions between protons result in a deuterium nucleus. In the sun, this is a problem because there are so many protons, and the even reaction this rare happens all the time. But on Earth, researchers rely on more easily reproducible reactions. But on Earth, researchers rely on more easily reproducible reactions, where a deuterium nucleus fuses with a tritium nucleus. A deuterium nucleus fuses with where deuterium nucleus fuses with a tritium nucleus to form a helium-4 nucleus, a neutron. We actually been doing reactions like this one inside particle accelerators since the 1930s. But these accelerators are not designed to harness the energy this reaction releases. Rather, these are used to generate neutrons for a variety of scientific and military purposes. Whereas, if we want to use fusion to produce limitless energy, we need a device that can harness the energy released, channeling enough of the energy back into the device to keep the reaction going, and then send the rest out to the power grid. And for that job, we need a nuclear fusion reactor. Like a particle accelerators, a reactor would generate helium nuclei and neutron, but that reaction would happen in a super hot core, and the resulting neutron would shoot outward and heat up the layer of lithium metal. That heat would then boil water, generating steam to run turbine and produce electricity. Meanwhile, the helium nuclei would stay in the core and climb into other nuclei to keep the reaction going and the electricity flowing. This tech has many practical challenges, including how to confine a swirling mass of million-degree matter. But the biggest hurdle is achieving what's called ignition. Energy technology is only commercially viable if out put out more energy than it uses. The fusion reactor needs a lot of energy to get a reactor needs a lot of energy to get the core hot enough for fusion to occur. So there's a tipping point, a moment where fuel is hot enough to start the reaction and releases more energy than is needed to reach and maintain the temperature. This is ignition. Start reaching ignition under the force of huge amounts of gravity. But this approach is impossible on Earth since you need certain times of mass of, well, the entire Earth. So researchers typically rely on best arrays of lasers or methods that combine magnets with high energy particles or electromagnetic waves similar to those in your microwave oven. In 2023, In 2022, scientists at the U.S. National Ignition Facility demonstrated ignition for the first time ever, using 192 lasers to heat deuterium to 100 million degrees. While this was a huge step forward, we're still ways off from self-sustaining long-running reactor that produces more energy than it uses. But once operational, this relatively small reactor could power a city of 1 million people for a year with just 2 pickup trucks of fuel. Today, you had to burn roughly 3 million tons of coal to produce that much energy. That is the promise of fusion, limitless on-demand energy with almost no emissions. Two-star power right here on Earth.